Ever wondered why a straw in a glass of water appears bent, or why a mirror shows a reversed image of you? Today, we're diving into the exciting world of light to find answers. Light, an everyday phenomenon that illuminates our world, is a fascinating subject that physicists have been studying for centuries. It has properties and behaviors that can seem strange and counterintuitive, lending a sense of mystery to the science of light. In this video, we'll explore some important concepts related to light, such as reflection, where light bounces off surfaces, and refraction, where light bends as it passes through different media. We'll also delve into the intricacies of mirrors and lenses, which manipulate light in unique ways, and how our eyes, the natural lenses we carry with us every day, use these principles to help us see the world around us. So, buckle up as we start our journey into the fascinating world of light. We begin with a simple yet fundamental concept: reflection of light. Picture this: a ray of light traveling in a straight line until it encounters a surface. What happens next? It bounces back. This phenomenon is what we call reflection. It's guided by two main laws. First, the incident ray, the reflected ray, and the normal to the surface at the point of incidence all exist in the same plane. Second, the angle at which the light hits the surface, known as the angle of incidence, equals the angle at which it bounces back, or the angle of reflection. This isn't abstract science. It's happening all around us, all the time. Every time you see your reflection in a mirror or the glare of a shiny object, you're witnessing the laws of reflection in action. So the next time you look in the mirror, remember the laws of reflection at work. Now let's add a curve to the mix and explore spherical mirrors. You know, mirrors aren't always flat. Some mirrors curve inward or outward, and we call these spherical mirrors. There are two types: concave and convex mirrors. Concave mirrors curve inward, like a cave, hence the name. When parallel rays of light hit a concave mirror, they converge at a point known as the focus. On the other hand, convex mirrors curve outward. When parallel rays of light hit a convex mirror, they diverge or spread out. Now let's talk distances. The distance between the mirror and the focus is called the focal length. It's represented by the letter F. The distance from the mirror to the object being reflected is known as the object distance, represented by U. And the distance from the mirror to the image formed by the reflection is called the image distance, represented by V. But how do we connect all these distances? Enter the mirror equation. The mirror equation, expressed as 1 over F equals 1 over V plus 1 over U, is a handy tool that lets us calculate any one of these distances if we know the other two. For instance, if we know the focal length of a mirror and the distance of an object from it, we can use the mirror equation to find out where the image of that object will form. Conversely, if we know where an image forms and how far the object is, we can use the mirror equation to find out the mirror's focal length. This equation isn't just a mathematical curiosity. It's a fundamental tool that optical engineers use to design everything from car rearview mirrors to high-end camera lenses. So, the next time you look into a mirror, remember, it's more than just a reflective surface. It's a carefully designed tool that follows a precise mathematical relationship. So, spherical mirrors aren't just funhouse mirrors. They're a critical part of understanding light. Scene script. Ever seen a rainbow? That's refraction of light in action. Let's dive into the concept of refraction. Imagine light as a marathon runner. As it races from one medium to another, say from air to water, it doesn't always keep a straight path. Instead, it changes its speed and direction. This bending of light is what we call refraction. Now, this isn't random. It's governed by a neat little principle known as Snell's law. Picture light hitting the surface of a pond. Snell's law tells us how much the light bends when it enters the water. It's like a mathematical recipe. The amount of bending, or refraction, is determined by the angle at which the light hits the water. That's the angle of incidence. And the properties of air and water. These are the refractive indices. So in the language of Snell's law, we say that the refractive index of the first medium times the sine of the angle of incidence equals the refractive index of the second medium times the sine of the angle of refraction. But what does this mean in real life? Well, whenever you see a straw seeming to bend in a glass of water, or when you notice the shimmering mirage on a hot day, or even that enchanting rainbow after a spell of rain, you're witnessing the fascinating phenomenon of refraction. Each color in a rainbow, from red to violet, is essentially light refracting or bending as it passes through millions of raindrops. And since each color in white light bends at a slightly different angle, we end up seeing them spread out into a beautiful spectrum of colors, a rainbow. So the next time you spot a rainbow, you'll know exactly what's happening. Now let's focus on lenses. Ever wondered how a magnifying glass works? Well, lenses, like mirrors, also manipulate light, but in a slightly different way. Instead of simply bouncing light off, lenses refract or bend light. This change in direction occurs because light travels at different speeds through different substances. There are two main types of lenses. Convex lenses, which are thicker in the middle than at the edges, converge or bring light rays together. This is why a magnifying glass, which is a convex lens, can focus light to a point and magnify images. On the other hand, concave lenses, which are thinner in the middle than at the edges, diverge or spread out light rays. Now, just like mirrors, lenses also have a formula that relates the object distance, image distance, and focal length. It's quite similar to the mirror formula, but with a slight twist. The lens formula is expressed as 1 over the focal length equals 1 over the image distance subtracted from 1 over the object distance. This formula allows us to calculate any of these three variables if we know the other two. There's another important concept related to lenses, and that's the power of a lens. The power of a lens is simply the reciprocal of its focal length. It's expressed in a unit called diopters. A lens with a high power has a short focal length and can bend light rays more sharply. Conversely, a lens with low power has a longer focal length and bends light rays less sharply. Understanding these principles of refraction by lenses and the power of lenses helps us to understand not only how everyday objects like glasses or magnifying glasses work, but also more complex systems like telescopes and microscopes. So lenses aren't just for glasses, they're integral to understanding light and its properties. Your eyes are the best camera you'll ever own, but how do they work? Let's journey into the fascinating world of the human eye, a marvel of nature that functions like a well-crafted lens. At the front of the eye, we have the cornea, a transparent layer that helps to focus light on the retina. Just behind the cornea is the iris, the colorful part of our eyes that controls the amount of light entering the eye. It does this by adjusting the size of the pupil, the black hole in the center of the iris. Then we have the lens, situated behind the pupil. The lens is a flexible structure that can change its shape, allowing us to focus on objects at different distances. This ability to adjust focus is called accommodation, and it's controlled by the ciliary muscles that surround the lens. The light then passes through the vitreous humor, a clear gel-like substance that fills the space between the lens and the retina, and finally hits the retina, the light-sensitive layer at the back of the eye. The retina contains millions of photoreceptor cells that convert light into electrical signals, which are then sent to the brain via the optic nerve. Now, despite this incredible system, our eyes can sometimes develop defects. Two common ones are myopia and hypermetropia. Myopia or nearsightedness is when the eye overfocuses and images are formed in front of the retina. This makes distant objects appear blurred. On the other hand, hypermetropia or farsightedness is when the eye underfocuses and images are formed behind the retina, making close objects appear blurred. Thankfully, we can correct these vision defects with the help of corrective lenses. Concave lenses are used to correct myopia by diverging light before it enters the eye, and convex lenses are used to correct hypermetropia by converging light. So, our eyes are not just windows to the soul, they're intricate optical systems. Through understanding the human eye and its defects, we can appreciate the incredible gift of vision and the science that helps us see the world more clearly. We've journeyed through the world of light, from reflection to refraction, mirrors to lenses, and even our own eyes. We've explored how light travels in straight lines and reflects off surfaces, following laws that dictate the angles of incidence and reflection. We've discovered the role of concave and convex mirrors and how to calculate image and object distances using the mirror equation. We've delved into the bending of light as it moves from one medium to another in a process called refraction, guided by Snell's law. We've seen how lenses both converging and diverging manipulate light and how their power is determined by the reciprocal of their focal length. We've even looked into our own eyes, understanding how they function like converging lenses and learning about common vision defects. So, The next time you switch on a light, remember, there's a whole world of physics illuminating your path.